Okay, do you remember? We were talking about this multi-dimensional corridor of a normal operation or safe operation, going out of safe operation until we have a failure. And we have a fault here, and there is a latent time until we see the effect of the fault, or even we see the effect. Now, let's see more details about this graph. Here, now in a two-dimensional space, do not forget the normal state space of a normal machine is maybe a 100-dimensional space, because we have maybe 100 different variables, or even 1,000 different variables which define the state of the system, or even much more. But in this case, let's take only two, so we have a two-dimensional space. Okay, this is the start of the operation of the system, and it shall stay here in the green region. So it's moving everything right, and here at this point we have a malfunction, a bug detected, a bug is activated, or we have a fault. This will be the case if we are talking about software, then a bug was activated, and a fault occurs if we are talking about hardware. Okay, so, but immediately doesn't occur anything. Immediately the system continues working for a small time, and this is the error latency time. So there is a time until we see that something is going wrong. And here we have the first error detection. Here we know something has gone wrong. And maybe from here we have time to make a control shutdown, or safe shutdown, or fail safe, or fail soft, or send a warning, or anything. Here we have the time. And from here, maybe we lose control of the operations of the system. So it begins maybe oscillating or doing who knows what. It crosses the warning area, and then we have a failure at this point. And from here to here, we have the failure latency time. So first we have the error latency. So the first error occurred here, or the first fault. Here we have the detection, and then we have a time, that is the failure latency time, until we have the failure. And if we have no control, then maybe we have an accident. And there is another time from the failure until the accident. At this point, it was the system failure. Okay, so is the normal way from fault until accident. And now let's consider the case of software. Do you remember at the beginning we said there is a difference if we are talking about software or mechanical components or electronic components. So in software, everything begins with the error. In the other components, everything begins with a fault, and the error is the consequence of the fault. But here, from the beginning, we have an error, a programming error, a bug. So, but normally the bugs are sleeping. So they are already there, but as long as this program is not activated, they are not triggered, they keep sleeping. So there is no problem. We can have thousands of bugs as long as they are not activated. But at this point, something occurs, and we touch this bug, and it's activated. Then it makes something wrong, a wrong operation, and then we have an error situation. So from here, the system is doing something wrong, and then we have a chain. Not only maybe one variable is wrong computed, and this variable produces a function to deliver a wrong value, and this will be propagated and growing until we have errors in all systems. So at the beginning, maybe a small error, but it will be propagated, and at the end of the chain of these errors, we can have the failure. So we have the case from sleeping bug to the activation to the explosion. So it's if we talk in software. Okay, how is the way from an error to an accident? Okay, here we have the normal operations. So everything is going normal, and then we have a failure, an error occurs. Then we can have an erroneous situation, and maybe we have a fault tolerance or something to handle this error. Then we can come back to the green area to normal operations. But if we have this fault tolerance not implemented, or we have no chance to control this, then we have two possibilities. The best is we have a fail-safe, So we control the system until we stop it. So slowly reducing the functionality until we bring it to a safe situation, and then we can stop. Then we have a fail stop. And this is not a bad situation. So the base is fault tolerance, so we can continue the operations. If not, we shall have at least this fail safe to avoid the accident. We stop providing the service, but we avoid accidents. But if this doesn't work or is not implemented, then there is no handling. Then we have two possibilities. If we are in luck, then we have a system error without consequences, or if we are not in luck, then we have an accident. And from the accident, then we have the situation, we shall do something to limit the damage. So the accident is already done, the damage is coming, but we can implement more functionality to limit the damage. That is the case of the airbag. Okay, we were not able to avoid the accident, but we protect the drivers. Okay. And now let's talk about this failure propagation. First, if we are talking about hardware. This is our normal system. That is the system has modules, the modules has submodules, and so on, until very small components. For example, a screw, a very small component of a very big machine. Green means it's working properly, and rot, something has failed. And let's assume a very small component, a screw, it breaks. And if this breaks, then maybe this submodule will not operate properly. Okay, maybe something will stuck, not work anymore, and then this submodule has failed. But if this submodule fails, then the next module who requires this functionality will fail too. And if this module fails too, because this functionality is not coming, then it will propagate until the total system. So the aeroplane. The whole aeroplane can fail because a small screw breaks someone in a submodule. So we have this error or this failure propagation from small fault to the failure of this submodule, to the failure of this module, to the failure of the complete system. Okay, this is when we are talking about hardware or mechanical components. When we are talking about software, then there is something different. Then we have a failure propagation in the data path. Okay, which module is consuming data from which other module? It doesn't matter the hierarchy which the module is built in, but which module is producing data or services for other modules. Let's assume this is our data path. This module is computing something, for example, air speed. And this air speed is used for autopilot to keep the normal speed, and for display, and this is used by the board computer to compute the FAT and so on. Huh? And this module computing the airspeed fails. And then the next which is going to fail are the modules which are using data from this other module. So we are propagating this. And if these modules has failed because they are using ground data, then they are going to propagate ground data and the next module will fail. So we have a failure propagation. Just a second. Yes. We have a failure propagation along the data path, not where the module is built. So like before, just a second, like before, it's not important which module is built in which other submodule, but which module is consuming data from which submodule. And that is the difference. We are talking about hardware and software, how the failure is going to be propagated. And we have one more scope of failures or faults. Do you know which? We have already a mechanical or electrical. We have software. There is one more. Communication. Yes, we have another scope of errors or faults, and these are error in communication. Okay, we have different types of communications error. The most specific, clear to see and easy to handle is crash. One module is going to crash and stop sending data. So it sends no wrong data, it says absolutely nothing. And this is easy to handle because the module is not responding anymore. We can start another module and continue and continue working. This is the most specific. So the node just stops without undergoing any incorrect transitions. The next, more difficult is the node doesn't stop. It continues sending, but sending wrong data. This is much more difficult. So the system is working, but with wrong data, and this can propagate failures along the data path, or use omission of some data. Sometimes it answers, sometimes it's not answering. So it's difficult to handle, because if you ask, "Are you still alive?" he answers, "Yes, I'm still alive and I am working." Then you send a request and you get nothing. Okay. More difficult to handle are timing errors, and maybe timing and data errors. So one node is still answering, but maybe too early or maybe too late. So in worst case, you don't know if the data from this module corresponds to the cycle before, or the next cycle, or to the current cycle. So these timing errors can be difficult to handle. And the most terrible case of failure is what we call the Byzantine types of error. And this is a totally arbitrary behavior. Really difficult. The node is responding, the node is sending data, but wrong data, and more difficult, different data to different nodes. For example, if this node is producing data for this node and this other node, the worst case is it sends something to this and something different to this. And then there is a very big conflict, because the data will not be consistent and no one knows who is wrong. This module, or this module. So this is the worst case of communication errors. Okay, now we know we have a fault, and if we do nothing, do you remember? We have a fault or malfunction. If we do nothing to avoid this, then we are going to land here in an accident. So going down is very easy. So here you stumble, and if you do nothing, you are going down and down and down, and you have the accident. So we can feel like maybe we cannot avoid this stumbling, but we shall be ready to handle this to avoid the accident. Okay, this is the error handling, what we have to do. First, something occurs, there is an error. First, there is a fault. On this fault has an error, and this error is not normal situation, not normal behavior. The first thing we have is a error detection. As early as possible to detect something is wrong. If we do not detect the error, then we cannot stop the accident. We will continue until we have the accident. Okay, after you have detected the error, you have to report. And some other module shall know something is going wrong, and maybe this is the point to report to the operator, warning something is wrong, be aware. Then we have error isolation. If we know some module is producing bad data, to avoid this data to be distributed in the system. So stop this module, or isolate, or turn the communication off, or send a warning to all other modules, please don't use the data from this module because it's corrupted, it's doing something wrong. So the error isolation, to avoid the propagation of the error and to avoid the propagation of the error. And then we need an error handling. Okay, we know something is wrong. It's already, so everybody, the warning was issued already. Everybody knows, or this module is off. Then we have to do something to handle this error. For example, turn the failed module off and turn another module on. And then error correction and return to normal operations. Okay, this is the chain of operations we have to do to avoid an accident or to avoid a total failure. If one of these is failing, this is a chain, all of them has to be working. If one is failing, then we cannot avoid the accident or the failure. Okay, the strategy for failure prevention. What shall I do? First, quick malfunctions diagnosis. If something is not working properly, as soon as possible identify what is going on. In order to take the action, you have to know what is wrong. Then you need an effective isolation of the malfunctioning elements. That is this here, to avoid the propagation of the errors. And then maybe the best thing is online repair. Maybe you had hot spot or hot redundant models, so two models are or three models are doing exactly the same, and if one fails, just ignore and the other models continue working. Or maybe you have cold redundancy. You have one model working and you have other models, but they are off. So you have first to turn this off to avoid the propagation of the error, to turn the next on, send the current state, synchronize this node with the system, and continue working from this point. And then do anything to avoid catastrophic malfunction. So stop working or do anything, but avoid an accident. This is the most important part. Okay. Okay. And I said before, going down is very easy. The difficulty is to stop this and go up again. This is the way going down. We have the ideal system, everything is working properly, and if something goes wrong, then we have this chain going worse until we have failed or the accident. And very important is to stop at one point and maybe to go back. And this is difficult. To stop is difficult, you know, when you are going down, to stop and then to recover. For these names, I looked for translations, and these are the translations, and I found these two translations are the same. So I'm going to explain what is the difference, but if you take a look to the translations, it's the same. Okay, first we have the ideal situation. The system is working properly. Then something is defective. This is a fault. Something doesn't work anymore. Maybe a screw has broken or something like this. But up to now, nothing has occurred. We have already a faulty situation, but it has no consequences. At this point, we have the consequences. The screw was broken, and now something is not working. Something is stacking, clack, doesn't move in anymore, or going away. And this is the faulty situation, what is not properly. And then we have the erroneous situation. Then the system is providing wrong data, or moving in a wrong direction, or doing something wrong. This is the erroneous situation. Then we have the malfunction. The system or this module shall provide some data or some service or some movement or some forces, and now is providing something different. Maybe nothing, or maybe something wrong. And then we have the situation, we can continue working, but degraded. Maybe we have some modules which produce a force to move something, and one has failed, then it will not be used anymore, but other modules can produce the force and it continue working, or redundant data. But if it isn't works, then we continue falling down and then we fail. The system has failure. So this is the chain from from the ideal performance going down until fail. And our task is to stop as early as possible and go back to the ideal situation. And as deeper we are going, the more difficult will be to stop, and the longer is the way to come back. So if we stop, we stay in this state. And the best thing is we don't stay long, we go back here. Okay, the definition again, working properly, this is the ideal situation. Here, having a defect of flow, imperfect from structure or function, imperfect, but it can work, maybe a software bug. Here, is this imperfect in faulty? It is defect and dangerous, does not work properly, but it has no effect until now. It's only inside of the module. Wrong computations, but no effect until now. Then we have the erroneous situation. Something went already wrong. Inactive, incorrect, inexact, or invalid data, but still internally. Then it fails to operate normally. Now it's visible. It's not provided the service. Up to now it was inside of the module. From here we see outside of the module that the module is doing something wrong. So from outside we can see something wrong. And here, in this case, the best we can do is continue operation with lower performance. And if this fails, then we have the failure in operation, or maybe an accident. Okay. In this chain in this chain of operations, we have different levels. But first, we have here the entry. We begin here in this situation. And going down is a deviation. So it's not doing what we expect. So every time we have a deviation, we get deeper and deeper and deeper going down. If we stay in this level, then we have something like tolerance. So we can stay there. We can tolerate the error or the ground function, but we don't go deeper. And the best thing is we have a remedy. We repair the problem and we go up. And if we look at this graph, at this chain, we can recognize we have a low level area. This is from module, from device. We have a middle level, that is state of the system. And we have the high level, that is the whole system. So in the low level, from here to here, we are handling with the results, going down to logic. In the middle level here, we begin from logic, going to state of the system. And the high level, we are talking about a service or the result which the system shall produce. Okay. And we can propagate this in the system. Let's go back a few slices. Something like this. Maybe we are talking only about one module. One module is going to do this change from normal operation to failure. And this is going to propagate to the next module or to the next module. And in software, going from ground computations to many modules have failed. Okay, now let's see how it works. How it doesn't work is better said. Okay, let's take this chain of events, and this chain can be from module 1, and when module 1 fails, then it produces a faulty state for the upper level module, and we begin at this point. And when this fails, we begin at this point, faulty, for the next level. And so we can propagate an error or malfunction from a small component to the whole system. Okay, and I said before, going down is very easy. Just do nothing. Do nothing to avoid, and then you are going down from here up to down, from a small failure up to total system failure, if you do nothing. More difficult is to go up again. And what we have to do to the repair? Okay, first at this point we have to detect and diagnose the malfunction. At this point we have to remove the malfunctioning unit. For example, we have to update the system tables. Maybe it's in operating system, so we have system tables who says which module produces that, and or if in communication way, which way to go going from this node to this other way. So we have to update these tables to go around the failed modules. Maybe some kind of physical isolation, if we are talking about physical machines, structures, or initiate and repair if applicable. Okay, then the next step here, create a new working configuration. Here we have isolated, we avoid the propagation of the error. But now we have to go back to normal operations, so we have to create a new working configuration without using the failed module. So exclude processor, channels, or controller, or IO devices, or sensors which have failed. Avoid any communication with these devices. Is, let's say, noisy communication. Avoid links and ground messages propagation from the failed devices. You know, here you recognize the failed module, here you have isolated, and here you have to avoid any communication with these modules. And then maybe remove the parts of the memory and address mapping. Okay, and then the next you have to do is recover the process and associated data. Maybe data was corrupted, maybe there is a way to recover this data, redundancy, and the process. So if possible, recover the state, the right state information of the process which we are doing, and then reactivate this process with this data. So you have to synchronize the process after starting with the current data, and then you have recovered. Okay, and this is the same chain which we saw before. There is something more. we stop a failure, but we can go deeper. So going down, we said, okay, we have a failure and this is the deepest position, but then after the failure, you can have an accident. If it is going worse, you can have a disaster, a very terrible situation. So going from failure to accident to disaster, the example of this space shuttle, maybe you know, the space shuttle Challenger, it was a disaster, so it was an accident and it was a disaster. All these astronauts died, and this was the end of the space shuttle era. And what was the source of this catastrophic, of this disaster? It was a gummy ring like this, and isolation in the boosters. And it was cold, and these days, and then the ring break, and then we have we had a fuel escape, and then we had the biggest catastrophe. So going down from a small component to an accident and to a disaster. Okay. And of course, we want to avoid accidents and disasters, so we have several layers of safeguards. So only one layer maybe can help us, but in very critical systems we shall have several layers. But in any case, we cannot be sure no accidents will occur, never. Because let's say every layer is not perfect. It shall recognize some failures, and then, but let's say 1% of miss, 1% of all situations which are wrong will not be recognized as wrong. But then you have another layer, and this layer shall do the same. But if you have a common root failure or bad luck, then maybe some failures which are not recognized by this will not be recognized by the next. And then you can add several layers of protection, but there will be always some cases which exactly the same situation is not recognized by all layers. The probability is very low. Let's say if you have here only 1% of miss, and here 1% and 1% of person, after 4 layers of protection, you have 10 to the power of -8 of probability of not recognizing the error. And this is a very low situation. Probability. For example, 1%, that means 1 to the power of 2. 2 times this will be 1 to the power of 4, of 8, and 16. So the probability of this miss going through all layers shall be almost impossible. Well, but if you take a look to the reality, that's not the case. So we have so many systems with 4 layers of protection, and despite of these 4 layers of protection, we have an accident. The reason is these holes, which are not perfect in the layers, are not really randomly distributed. They are done by maybe different programmers, and different programmers are the same type of humans, and they are making the same type of mistakes. So we have seen some statistics, some analysis of mistakes done by different programmers in different regions, and they are the same. So if 2 persons are programming this, you cannot be sure that they are not going to do the same mistake. Therefore, we cannot say, okay, the error which are not recognized by this layer will be recognized by the next layer. People tend to do the same type of errors. Okay, now which measurements can we take to provide higher dependability? What we want to avoid in the first case is a disaster or an accident. Okay, maybe we reach this situation, failed. But in any case, we shall avoid going down to accident and disasters. Okay, in any case, in the worst case, we shall stay here, tolerate all failures and stay in fail, but do not go deeper. How can we do that? Okay, something went very wrong. We did our best to avoid the failure, but we have a system failure. Now let's stay here, don't go deeper. What can we do? For example, in aeroplanes, there are manual control and override of the controlling system. So There is a paper information which says the pilot what to do and disconnect all control computer, disconnect all automatic systems and do it by hand. Maybe it will be able to recover the accident. Or in case of spacecraft, satellites or some, turn off all automatic systems and do it by hand. Or manual bypassing nuclear reactor. So if the system has failed, then do it by hand. Open valves for cooling and turn off the reactor. So everything done by hand without the control system because the control system has failed. So we have here the last chance to avoid the accident, the last chance doing a manual recover. Or maybe we have a manual backup system, everything mechanically done by people, or provide a buffer between the failed state and the potential disaster or accident. This is something we can do here if everything else has failed and we come here in the system failure. Or we were not able to avoid this. Oh, then we have an accident. But still, we shall do everything which we can to avoid the disaster, to protect the pilot, to protect the people. These are typical cases. We can say up to here we did everything to avoid the accident, but the accident occurs. Okay, then what can we do? For example, airbags, or get a fire extinguisher ready so everything is burning. All measurements to avoid this didn't work, but the operator can take the fire extinguisher and do something, or evacuate. Alarm, go out. Or emergency call, automatic emergency call. And this is something we can do after the accident to avoid the disaster. Okay, we have active and passive measurements, what we can do to avoid the disaster. The active measurements is where the board computer can help. So program and control systems, and this is before the accident occurs. Or if the accident is inevitable, you see, okay, it's not possible. If you control, take a look to the speed and when the collision is going to take place, and you know, according to the physics, you cannot avoid this. Okay, then do everything you can to reduce the damage. For example, auto brake. The first for, let's take the example for cars, to keep the distance. This will be an active safety, and if you see you cannot avoid the collision, make the biggest brake you can do. Or you have some sensors all around the car to detect if someone is moving around the car, and if someone is moving or some unexpected things are moving here, make a brake. So this will be an active measurement for active safety. Then we have passive safety, and this is done by construction. For example, after the accident, we can have something like a crumpled zone. So here, after the accident, if you have here a bigger crumpled zone, then the acceleration here inside of the cabin will be lower, and the probability to survive will be a little bit higher. Or something like airbag, passive after the accident, used to limit the damage. Now let's see some analogies. Okay, we have here a bug. The bug produces an error. The error produces a malfunction. The malfunction produces a failed module. The failed module produces an accident, and then the disaster. So we have here the bug. Something was wrong from the beginning. Then you stop, you stumble, you fall down, and here you have the passive or active safety. So you cannot avoid the accident, but to reduce the consequences of the accident. So after this, we have two possibilities: limited damage, active or passive, then you have some injured, or if you have nothing here to reduce the damage, then you are dead. Okay. Or active safety, the Kung Fu modus. So even if you are flying, you apply your Kung Fu and you fly back and you stay again. This will be the passive safety about this system. Okay, a second analogy. Now let's take this analogy looking at a car, the braking system of a car. It begins with a defect. The brake fluid pipeline has a weak spot, or joint. So there is something wrong in the brake fluid pipeline. Then we have a fault. The brake fluid starts to leak out, so we are losing hydraulic. Then we have the error. The brake fluid pressure drops too low. From this error, we have the malfunction. The braking force is below expectations. We cannot brake as expected. And then we have two cases. First, degradation. The braking, we can still brake, but requires higher force to take long or takes longer. So you have to press with more force or it takes longer. But it's degraded, but it's still working. And we have the failure. The vehicle does not slow down anymore or stops anymore. So you can push the brake and nothing occurs. And this is the failure of the braking system. And after this failure, if you cannot brake, maybe you will have the accident, or in worst case, you will have a disaster. Okay, here you can see from a defect going down to an accident, or yes. And now let's take an example about degradation. It is still moving, it's still working, but not as expected. So this will be the normal operation. You can run very fast, and this will be the degraded operation. So you are still moving, but not as expected, with a lower speed and not so nice. So in any case, with the degradation, avoid to go deeper, avoid total system failure, avoid accidents, and avoid disaster. This is what we implement when we are talking about degradation of the system. Okay, how does it work? The first thing you have to do is to make a diagnosis, to know what is not going right. So diagnose the malfunction of the system and provide the capability to the system to work without the modules which are malfunctioning, which has failed. So this diagnosis says this module has failed and should know how to continue working without these modules, or even better, to substitute these modules. Okay, this is the degradation management. First, you have to adapt. If you have, for example, let's talk about computer. Let's compute in power, because some modules has failed. Then you have to make a new prioritization, priorities of task and redistribute the load. So now maybe you have less computing power than required, so you cannot execute all tasks anymore. You have to make a priority and say, this is the task I need to survive, to keep moving, and these tasks are just nice to have. We can turn this task off. So applying priority of task, or this low priority task will get CPU time only very little or almost nothing. Then you have to monitor the system. You have to keep track of system operations in degraded mode. So you have to see if the resources, the new distribution you did, is still enough to provide this service. Then you shall try to return to system to operations to system to intact, so to normal operations as soon as possible. You shall try, and then go back to normal operation. And this is the difference. You can adapt here with new reduced performance, or you can go back to normal operations, which is much more difficult. Okay, and this is how it works. This is the timeline, and this is the functionality or the performance of the system. This is the best case intact operation, what you shall know. If something has failed, then you can reduce your performance, and then you have a degraded systems until here. Or if system got worse, then you can reduce your performance, and then you have partial fail. Not totally fail, but it's not working anymore. And if something was wrong, then you are going to the crash situation, and then you have the failure and no performance anymore. Okay, what to do? So you have an intact system, something was wrong, and then you reduce your performance. This is a fail soft operations. So you continue working with degraded operations. Or maybe you have another failure, and then you reduce your operations again, and then you continue working. And then you have two options, or if you have the options, you can repair, online repair. So you continue providing this degraded function, and in the meantime, in the same time, the system is going to be repaired. The failed modules will be substituted or something like this, and then we can continue here at this point. we can repair the system and continue with intact operations. Or if we are not able for this online repair and the failures continue to occur, then the degradation will be higher until we get to the crash situation. And in the crash situation, if we have no accident, maybe we can perform an offline repair. So the system will be stopped after the crash. If we are lucky, we have no accident, the car has stopped, and then we can bring the car to the shop. It will be repaired offline, and then we come back to normal operations. Okay. Okay, now let's talk about what to do. Do you remember we said it will be not possible to reach 100% dependability? It's not possible. You know it will fail. You know the probability of failure. Then the question is what to do. What can we do to reduce the risk? What we want is to avoid an accident. A failure, okay, it will be there. But what can we do? We shall be ready. We know it will fail. The only thing we don't know is when will it fail. If we will know this time point, then everything will be ready. At this time point, stop everything, and it's done. But we don't know it. A very nice thing is if we can say before this point arrives, warning, I am failing now. Okay, what can I do? First, to improve, what can I do to improve the system to reduce the probability of accident? Now, I am not talking about the probability of failure. Failure will come. I am talking about the probability of an accident. Okay, a bad thing is these small failures, which are difficult to detect, shall be removed. It is better to have a big failure which is detected, which you can see immediately, than to have a small error which you cannot see and will stay there until you have an accident. So it's better to have big errors, big failures. Remember, it's better failures which are easier to see and to detect, even if they are bigger. And something important, unneeded system complexity shall be reduced. Do you remember one of the main causes of failures and accidents is higher complexity, because complex systems will fail and can fail in many different ways. Okay, and another bad thing is the extended failure latency. So if something was wrong and it goes a long time until you detect an error, that's a very dangerous situation. In the case of Apollo Tryson, do you remember the error was 5 years before, and 5 years later you have the accident. So that's try to do everything to reduce this latency between the failure or the fault and the failure. So as soon as possible, so you can react faster, so you can detect it. And the same system to support fast failure detection. So if something was wrong, detect as soon as possible. And and try to have a failure monitoring at the same time when the function is going to be produced. So remember, I assume we will have the failure. What can we do to reduce the probability of accident or reduce the damage after the accident? Okay, and then we have different types of failure. The best thing is fail stop. If the system or a module is not working, it shall stop working. It's very bad if it is fail and it continues working, producing wrong data or producing wrong behavior. It's better if it does nothing, that's doing wrong things. Or much better, fail safe. Okay, it has failed. Do not produce the normal, or do not try to produce the normal services or the normal data, but produce something which is safe to stop the system. For example, reduce the speed until the car stops, or in the case of an atom reactor, turn everything off to avoid an atom accident, a nuclear accident. So fail safe, forget the normal service you have to provide something which is not what you expect, but doesn't lead to an accident. And in any case, remember, malfunctions tolerance is much easier if the failed module stops working. If it continues working and sending wrong data, it's much more difficult to detect. So if you can, If the system has failed, stop sending data. And what you can do to detect this is, for example, watchdogs. You have a periodic timing report, and if this timing report is not coming, then you know this system has failed. Or you have messages counter. You can see how many messages are coming from a module. If this counter stays, then you know this module has failed. Or you have a messages timings. So you know at what time you shall expect a message from every module. If these messages are not coming, then you know the module has failed. So it's easy to detect. A bad situation is the module continues sending trash data. Then you cannot detect using these methods, and you have a bad situation. Okay. At this point, we are going to conclude. Thank you.